Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Akmal, and today our group we will presenting about our group assignment on characterize and analytically the effects of dispersion on optical system through simulation. This is our this is my group members, which is Afrina, me myself, Muhammad Akmal, Noh Harith, and Nuri Sabrina. For the introduction, it will presented by Nurin. Next, methodology by Harith. Result and discussion will be presented by Afrina and me. And lastly, for the conclusion, it will be presented by Nurin.
Dispersion is a phenomenon that causes optical signals to spread out and broaden as they propagate through a medium. This can lead to signal degradation and transmission error. Chromatic dispersion is one of the primary forms of dispersion encountered in the optical system. It arises due to the dependence of the refractive index of a medium on the wavelength of light. Meanwhile, material dispersion and waveguide dispersion are two separate factors that combine that creates chromatic dispersion. Gaussian pulses are frequently used to represent optical signals. However, they are susceptible to pulse broadening and overlapping due to chromatic dispersion. Higher order Gaussian pulses are also susceptible to dispersion, but their temporal patterns may be less susceptible to broadening than Gaussian pulses. Dispersion can cause problems for optical system by creating pulse broadening and overlapping, which subsequently result in signal deterioration and transmission error. By overcoming the dispersion-related difficulties, optical system can achieve faster data rates, longer transmission length, and enhanced reliability in numerous applications, including telecommunications and data transmission. The objective of this assignment is to characterize analytically and through simulation the effects of dispersion on optical system.
Now, for the methodology of our assignments. Basically, we use OptiSystem, that is a comprehensive software design suite that enable us to plan, test, and simulate optical links in the transmission layer of modern optical network. Alright, for the first step of our methodology, we must define the parameters and the component that we want to use in our simulations. Basically, we must drag several component and parameters from the component library panel and drop at the layout. So then we can construct the circuit as expected and in step 2. After constructing the circuit, we must select the components to set our parameter for each component in our circuit. For the step 3, we choose optical Gaussian pulse generator and we change the component properties. As mentioned, the power we set to 0 dpm, frequency we set to 1550 nanometer, and the order is set to 1. For the next step, we set optical fiber component, the length we set to 0 kilometer. For the attenuation effect of the optical fiber, the third order dispersion and self-phase modulations are disabled. For by Fringer's type is set to deterministic, and the differential group delay is set to 0. So we repeat the step 3 for the time delay components, as the delay is set to negative 0.51 nanoseconds. And step 3 also repeated for the clock recovery components, that we tick the enable option to enable the components. For the bit sequence generator, the bit sequence is modified to the expected value that mentioned in the slide, and the sequence length is set to 16 bits. Now we choose the parameter options and select the samples per bit, and it's set to 266. Now then we can click the run buttons that is located at the top panel. Next one for the result analyzations. So basically there are two port that we must take note. It's a dual port optical spectral analyzer and dual port optical time domain visualizer. So basically we can witness the graph from that port. That is the input at the signal at optical Gaussian pulse generator and the output signal at the time delay. Then we place two markers on the signal at time delay precisely at half the head of the signal. Then the screenshot of the graph is taken to be included in the lab report. So after doing all the process, we repeat the step 5 until step 15 by changing the length of the optical fiber from 10 kilometer that at the first. Now we change to 10 kilometer, 20 kilometer, 30 kilometer, 40 kilometer and 50 kilometer. Then after we witness the results, the graph and so on, we repeat the experiments or simulations by changing the order of the optical Gaussian pulse generator to from 0 to 4. So we analyze all the data and recorded the data in our assignments.
For chromatic dispersion, the first question is calculate the time delay after 50 km of propagation between two frequency components separated by 2 nanometer and with a dispersion parameter of 16.75 picosecond per kilometer per nanometer. So time delay is calculated using the formula of total delay is equals to the dispersion parameter times propagation distance times frequency separation. And by plugging in all the values, we will have the answer as 1675 picosecond. For the second question, derive an expression for theta w as a function of theta lambda using c equals to w over 2 pi times lambda, where c here is the speed of light, w is the angular frequency, and lambda is the wavelength. First, we start by rearranging the equation, and then we consider the change in w in theta w as theta w and the change in lambda as theta lambda, as the equation here shows, and then we times both side equation by lambda and we rearrange the equation and we will get the final answer as shown here. The third question, for an optical pulse of constant phase propagating in normal dispersion fiber, which frequency components will be detected first to at the leading edge of the pulse? The answer is the lower frequency components will be detected first as they propagate more quickly and advance towards the front of the pulse.
Next, we will move to the broadening of Gaussian pulses. Figure shows the circuit connection of first-order Gaussian pulse, where we set the order number to 1 in optical Gaussian pulse generator. Full width at half maximum, or FWHM, is the width of a spectrum curve measured between those points on the y-axis, which are half the maximum amplitude. In OptiSystem, we can directly use markers in the time domain graph to calculate the FWHM of the pulse. For TFWHM, we will view it in time domain visualizer. Meanwhile, for angular frequency of FWHM, we will view it in optical spectrum analyzer. For question 1, we were asked to plot the TFWHM as a function of distance and to determine their relation. To plot it, we need to use the marker function in time domain graph to mark point A and point B as shown in the figure. The magnitude difference of x-axis of point A and point B is the value of TFWHM. To find the relationship between TFWHM and distance, we need to repeat the step with several distances. For 0 km, TFWHM is 50.20 picosecond. For 10 km, TFWHM is 51.61 picosecond. For 20 km, TFWHM is 63.86 picosecond. For 30 km, TFWHM is 67.40 picosecond. For 40 km, TFWHM is 67.82 picosecond. And lastly, for 50 km, TFWHM is 78.02 picosecond. From the data obtained before, we plot it to a graph TFWHM versus distance. As we can see from the graph, the path spread out or become broader as it travels a longer distance. It means that as the distance traveled by a path increase, it will also increase proportionally. This is because the group velocity dispersion or GVD is a function of wavelength. Thus, it will cause the frequency components of the path to spread out in time as the path propagates over a long distance within a single mode. For question 2, we were asked to plot the angular frequency of WHM as the function of distance and to determine their relation. We apply the same method as previous, but this time it in optical spectrum analyzer. To plot it, we mark point A and point B as shown in the figure at the half maximum amplitude. Same as the FWHM, we need to do it with several distances to find their relationship. However, as we increase the distance, we observe that there is no change to the spectrum or spectrum width of the path. The shape of output graph in optical spectrum analyzer also unchanged. Therefore, when we plot a graph of angular frequency FWHM versus distance, we will obtain a straight line perpendicular with x-axis. In this case, the value of angular frequency FWHM that we have obtained is 0.66 nanometer.
Okay, for the next experiment, we change the pulse of the Gaussian to the fourth order and plot the TFWHM as a function of distance. For the graph that we get, we experiment for 6 distance. When the distance is 0 kilometer, we get 50.22 picosecond. For the 10 kilometer, we get 24.19 picosecond. Next is 20 kilometer, we get 44.56 picosecond. And next for the 30 kilometer, we get 64.34 picosecond. For the 40 kilometer, we get 85.69 picosecond, and there is some interference intersymbol occur. And lastly, for the 50 kilometer, we get 108 and 6.67 picosecond. Next, we plot the output, the full wave half maximum versus the propagation length. So for this graph, when the Gaussian pulse is increased to the fourth order, at first the pulse compress and at a certain distance, in this experiment is 10 km, the pulse broadens linearly as the distance increase. Okay, for the FWHM of the fourth order, the Gaussian pulse spreads more rapidly than the first order because the first order Gaussian pulse has a asymmetric shape and a relatively narrow spectral width. Thus, when the pulse travels along the optical fiber link, it will experience dispersion that leads to a temporal spreading of the pulse. So for the first order, the effect is linear. So the spreading of the pulse is proportional to the distance traveled. Okay, for the fourth order Gaussian pulse, the shape of the pulse has more complex with additional oscillation in the time domain. So, with the higher order of terms in the dispersion expansion, such as third order dispersion and fourth order dispersion, it contributes to the pulse spreading, thus affecting the pulse to spread faster compared to the first order dispersion. Next, the question asked to explain the strange behavior of the full wave half maximum for short distance, and is the TFWHM is the best method for measuring spreading. We need to compare to the first order Gaussian and the fourth order, why it spreads much more quickly by comparing the spectrums of both, and we need to explain why. The FWHM exhibits an unusual behavior for short distance due to combined influence of dispersion and high-order Gaussian pulse. So, when a pulse travels over short distance, dispersion becomes more pronounced and resulting in increased spreading of the pulse. Determine whether the FWHM is the most suitable method for measuring spreading depends on the specific requirements and context. While the FWHM is a valuable metric for quantifying pulse spreading, it may not capture all aspects of change in pulse shape accurately. Other parameters such as pulse width at a specific amplitude or pulse energy may also be considered based on the application needs. So, by comparing the spectra of the first order Gaussian and the fourth order Gaussian, we can conclude why the fourth order exhibits significantly faster spreading. The spectrum of a Gaussian pulse represents the distribution of frequency components within the pulse. High-order Gaussian pulse have broader spectrum compared to the lower-order Gaussian. This broader spectrum indicates that higher-order pulse encompass a wider range of frequency components, and consequently, these additional frequency components experience distinct propagation characteristics, resulting in the accelerated spreading of the fourth-order Gaussian pulse compared to the first-order Gaussian pulse.
This assignment has helped the students to understand the effect of dispersion on optical system and how to mitigate these effects. To conclude, there are three types of dispersion, which are modal dispersion, material dispersion, and also waveguide dispersion, where all can lead to undesired signal changes. Modal dispersion is specific to multimode fiber, while material dispersion and waveguide dispersion occur in single-mode fiber. According to the findings of this assignment, increasing the order time derivative of Gaussian pulses results in longer pulse duration in the time domain. In the meantime, higher order Gaussian pulses exhibit a faster spread of the full width maximum compared to the lower order Gaussian pulse.